Hello, my name is Kiril Bangachev, and today I'll tell you about my recent joint work with Guy Bresler on sandwiching random geometric graphs and Erdos-Renyi. To begin with, what are random geometric graphs? This is a family of random graph models which are designed to capture network formation based on similarity of feature vectors. This is a phenomenon that we see all the time in the sciences and the real world. So, for example, in a social network, people are friends because they have similar interests, live in a similar location, or are of similar age. To rigorously study such networks, we need a rigorous mathematical model. And one such model is spherical random geometric graph, which has been studied quite a lot in the theoretical computer science community in the recent years. More concretely, every vertex in an n-vertex graph has an independent feature vector, which is uniformly distributed on the d-dimensional sphere. And once we have those vectors, pairs of vertices whose vectors are close enough form an edge. Specifically, whenever the inner product is above some threshold, chosen so that the marginal edge probability is p, we place an edge between I and j. So for example, here I've sampled 10 uniformly random vectors on the three-dimensional sphere and form the corresponding random geometric graph. As you can already tell, the edges of this graph are probably not independent. So for example, here we see two triangles, even though there are quite few edges. So why do triangles appear naturally in random geometric graphs? Well, suppose that vertices 1 and 2 are adjacent. This means that their feature vectors are close. Now, if vertices 2 and 3 are adjacent, their feature vectors are close. Hence, by triangles inequality, the feature vectors of 1 and 3 are also close. In practice, oftentimes the feature vectors are fully or partially hidden. This could be due to privacy considerations or simply because of lack of measurement. This gives rise to a lot of interesting theoretical tasks. In particular, one may ask, what inference can we do? To answer these questions, the most fundamental question one can ask, which is also prerequisite for all other statistical tasks, is whether we can even detect the presence of a random geometric graph structure in a graph. This is a question that has been studied quite a lot over the past 15 years and can be formalized in terms of hypothesis testing. So by observing an n-vertex graph G, we need to decide whether it is a sample from the Erdos-Renyi distribution in which each edge appears independently with probability P, which is in a sense an absence of structure because there is no dependence between the edges, or is it a sample from a random geometric graph? So what do we know about this question after 15 years? So here's a diagram with the state-of-the-art results. First, in blue, there is some region, depending on the probability of connection P and the dimension D, in which we know that detection is possible by counting signed triangles. As I said, we expect that random geometric graphs have more signed triangles than Erdos-Renyi. On the other hand, there is some regime in red in which we know that the total variation distance is close to zero, which means that no test separates those two distributions. Finally, there is some white region, which we haven't fully resolved yet, but last year there was some progress by me and Guy Bresler again, and we showed that the low degree advantage is close to zero. In particular, this means that there is no low degree test, and it's also some heuristic for computational hardness. Still, the white region has not been resolved till today, to the best of my knowledge, and it is a very exciting mathematical question. However, in this work, we depart from considering the total variation question, and in fact, we've asked, is total variation even always the right thing to compare? Here are some reasons why total variation might not be the right thing to compare. First, note that we compared random graph distributions with Erdos-Renyi, in part to understand whether it inherits some of the very rich properties of Erdos-Renyi, which people have studied over the last 60, 70 years. But for a lot of these properties, total variation is way too stringent, right? We don't really need closeness in total variation to show that the graph distribution inherits some of the properties. And as an extreme case, recall that quasi-random graphs are deterministic graphs, which still have some of the spectral or subgraph count properties of Erdos-Renyi. On the practical side, it's perhaps even more important to not consider total variation, simply because it's too unrealistic. We cannot expect that a simple mathematical model, such as the spherical random geometric graph, captures all the edges in a social network, right? So there are definitely are edges which are not explained by the simple generative model, or maybe in the sciences, we also have errors in the measurements, which means that some of the edges, even if they're explained, are not what we observe in the actual graph. So this is our angle, and in particular, we want to form a comparison which captures both these theoretical and practical considerations. So in particular, we'll aim to make a conclusion about all monotone properties. I'll discuss monotone properties in more depth in a little bit, but monotone properties are a very rich family of graph properties which has been studied a lot in the theoretical computer science and combinatorics communities. Similarly, I will want a comparison for which not all edges are necessarily explained by the random geometric graph model. So what is such a comparison? One such comparison is given by the sandwiching comparison. So the sandwiching comparison has been studied in prior work by Achleoptas and Kojoglan in 2008. And specifically, what do we mean when we say that we want to sandwich an Erdos-Renyi? We mean that there is some Erdos-Renyi with a slightly smaller edge density than P, some Erdos-Renyi H plus with a slightly higher edge density. Then we can couple with our distribution so that with our probability, H minus is a subgraph of G. So all the edges in the Erdos-Renyi with smaller density are part of our graph. And also all the edges of our graph are part of the Erdos-Renyi with the higher edge density. Again, here containment is defined by edge subsets. You can already see that such a comparison would address the desiderata, and part of why is that first we have this monotonicity in terms of edges, so we will be able to say something about monotone properties. And also know that there is no requirement on the edges between H minus and H plus, right? We have those two Erdos-Renyi graphs, which sandwich in between our distribution, but what exactly is in the sandwich between H minus and H plus? We have no requirements. So such a comparison is the main claim of our work. We show that such a coupling exists whenever the dimension is more than n times p. And we know that this is tight, so we can also show that when the dimension is less than n times p up to some logarithmic factors, it is impossible to couple in such a way. One remark is that this coupling addresses a mostly unexplored regime on random geometric graphs. So most prior work in the high dimensional setting focuses on the regime when the dimension is more than n times p cubed, because we know that when the dimension is smaller than n times p cubed, the two graphs are far in total variation distance. So we cannot conclude anything about random geometric graphs by comparing in total variation with Erdos-Renyi. However, our comparison kicks in at much smaller dimension, so we can compare in a much broader regime of dimensions. So now I'll present very briefly what the key proof ideas are, and then I'll proceed to some applications. So the proof of this result is an algorithm, and in fact an efficient polynomial time algorithm. So what is the main ideas? Let's focus on the case that we want to produce a random geometric graphs, which is contained in an Erdos-Renyi with a slightly higher edge density. The way we will do this is that someone will give us the Erdos-Renyi with slightly higher edge density. Then we want to produce the n feature vectors on the sphere and their corresponding graph G. And we want the following two properties. First, all edges of G are also edges in the Erdos-Renyi. And also, we want the feature vectors to be uniform and independent on the d-dimensional sphere. This is to ensure that the corresponding G is actually from the random geometric graph distribution. So how do we do this? What is our algorithm? We start by sampling and just independent uniformly random feature vectors on the sphere. These will not be the vectors that will output. The vectors that will output are V1 with a subscript 0, V2 1, Vn minus 1. And those will produce by going iteratively over our edges and modifying them. So specifically, we go in lexicographic order. So A is the vertex with the higher index, and then B with the lower index. And whenever we encounter the edge AB, we change the vector corresponding to VA measure preservingly in the direction of the vector VB that we will output. So measure preservingly, I won't say what it is, but I'll explain the significance in a little bit. This is to ensure the second property, and to ensure the first property, we want that the inner product of the current VA and the output VB is above the threshold, so that there is an edge. Again, the analysis is composed of two key lemmas. So the first key lemma is the distributional correctness. Because of the measure preserving property, for any A and B, the current vectors v10, v21, va minus 1, va minus 2, which are the ones that we output, and va, which is the one that we currently modify, are independent and uniformly distributed on the sphere. The second key lemma is that once we change a vector A in the direction of vector B, even after we perform some further changes on A, the inner product will not change much. And this is why, once we have an edge, things will not change much. Okay, I won't go into the proof. So the proof of lemma 1 is rather straightforward once we define correctly the measure preserving property. The proof of lemma 2 is quite more sophisticated, and it's based on expanding this difference and decomposing into a martingale part and a not martingale part, and then on the martingale part we do some martingale concentration. But for now, let's proceed to the applications. So the first application is on robust testing of random geometric graphs. So recall the testing question, which can essentially be defined as follows. On input G, we just test whether the graph is from Erdos-Renyi or is it a random geometric graph. In the robust testing, however, we allow for an adversary, and what adversary is allowed to do is just to change any epsilon n choose 2 times p edges. Note that n choose 2 times p is the expected number of edges in both the random geometric graph and in the Erdos-Renyi. So we scale in terms of the expectation. Why is that? Well, note that when epsilon is 0, this is just, the usual hypothesis testing, which people have been studying for 15 years. When epsilon is a little bit more than 1, one can actually erase all the edges in the graph, right? The adversary just removes all the edges. So both Erdos-Renyi and random geometric graph just become the empty graph. So this problem is even information theoretically impossible. So this means that the interesting regime really is when epsilon is between 0 and 1. And this is the problem we study, and observe that actually our adversary, which couples both GNP and RGG to the Erdos-Renyi with slightly higher edge density, are actually adversaries, right? So if we start with a random geometric graph, we know that we can add just a few edges and transform it into an Erdos-Renyi with higher edge density. And also, if we start with the Erdos-Renyi with parameter p, we can just add a few random edges and also transform it. So in particular, our coupling algorithm is an adversary, even an efficient adversary, which turns those two distributions into the same Erdos-Renyi distribution. In particular, an immediate corollary, so that when the dimension is more than n times p, the robust testing problem is information theoretically impossible. Turns out that this is tight, and in fact, we exhibit an efficient constant degree sum of squares program, which distinguishes the two graph distributions when the dimension is less than n times p, and they're at most epsilon times n choose 2 times p corruptions for any sufficiently small constant epsilon. So what is the main idea of the proof? I'm not writing out the SOS program, but the idea is that the hidden embedding vectors are a robust certificate for a large spectral norm of the central adjacency matrix of the random geometric graphs. So if you write down a SOS program, which is a certificate of the spectral norm, we'll be able to certify very different things for random geometric graphs and Erdos-Renyi. And we know that this essentially fully resolves the testing question with corruptions, constant times n choose 2 times p corruptions, but testing without corruptions is not fully resolved, right? This is the white region with which I began. Okay, so second application is on monotone properties and sharp thresholds, which is a much more combinatorial property of random geometric graphs. So namely, what is the setup? First, the monotone increasing graph property is just any subset of graphs which satisfy the property, such that if we have a graph in this subset, also any graph obtained by adding more edges is in the subset. which means that we cannot violate the property by adding more edges. Now, for any such property, which is not just all graphs, one can very easily show by continuity that there exists some critical probability such that if we draw a sample from the Erdos-Renyi with marginal edge density P critical, the property is satisfied with probability half. So in this diagram, suppose that the blue curve is the probability with which the property is satisfied for G and Q. And then the red line is the P critical. So if we draw with this probability, we'll satisfy the property exactly with probability half. Similarly, we are not restricted just to half. We can define it for any other probability. So for example, here we have the probability for satisfying with 0.1 and here with 0.9. Now, very important is that we say that P has a sharp threshold if we jump from very low probability, like 0.1, to very high probability in 0.1 in a very, very short interval. So interval smaller than this critical probability. What do we know about sharp thresholds? Well, it's actually one of the really milestone results in probabilistic combinatorics that under very general conditions, any monotone vertex transitive graph property exhibits sharp thresholds with respect to the Erdos-Renyi distributions. This is the seminal result of Friedgut, which builds on a lot of work before that. Now, note that one can ask the exact same question, for example, for random geometry graphs, right? They're also parameterized by some probability, or by Ising models and other spin systems. Turns out that overall, for non-product distributions, this question is much harder. However, our coupling result actually almost immediately gives sharp thresholds for random geometric graphs, right? What is the idea? Well, we show that the random geometric graph is itself between two Erdos-Renyi distributions with very similar probabilities, right? So the random geometric graph is sandwiched between two very similar Erdos-Renyi. So essentially, whenever the Erdos-Renyi jumps from satisfying the property with some probability to satisfying it with some other probability, random geometric graph will also jump. So it's actually almost only a matter of bookkeeping to show that when the dimension is more than n times the critical probability up to some log factors, then the random geometric graph also exhibits a sharp threshold for any property that the Erdos-Renyi has a sharp threshold. And we know that this is a new result, so all prior work only shows sharp thresholds for random geometric graphs when the dimension is sublogarithmic. And it is a major open problem on random geometric graphs to establish under what conditions they exhibit a sharp thresholds phenomenon. Okay, our last result is on enumeration. So again, this is our coupling result. And one particular corollary is that we can count the number of geometric graphs on n vertices in dimension D. So again, geometric graphs are just collections of points, such that whenever the points are at a distance under some threshold, we place an edge. And we show that the number of geometric graphs dimension D is at least e to the n times d up to some logarithmic factors. So what is the proof? It's actually almost immediate again from our coupling result. First, we choose P such that n times P is much smaller than D, such a way that we can really apply our coupling. But once we apply our coupling, this coupling actually implies that the random geometric graph and the Erdos-Renyi have somewhat similar entropies. And since we know what the entropy of the random geometric graph is, we can immediately translate it into a lower bound on the support size of the random geometric graph distribution. So this is the proof. We know that this is not a new result. So there is another recent paper of Lisa Zauerman, which establishes the same result, and even with a much stronger and tighter dependence on the logarithmic factors, which we omit here. But it must be noted that the tools used in this paper are much more sophisticated and come from algebraic geometry, while ours is a simple probabilistic construction. Hey, this is about applications. I'll finish with some open problems and directions. So know that what we did is we essentially show how to couple Erdos-Renyi and random geometric graphs in this way, where we sandwich the random geometric graphs between GNP1 minus epsilon, GNP1 plus epsilon for this specific epsilon, which is around square root NP over D. But this is the optimal value of epsilon, right? How small can we make epsilon? How tightly can we sandwich the random geometric graph between two Erdos-Renyis? And besides being, interesting on its own, this problem is actually also very relevant to the robust testing problem. So we fully resolved the robust testing problem with a constant fraction of n choose 2 times p corruptions. But we know that also the problem without any corruptions is still open. So what about, other epsilon, which are a function of the number of vertices? And while we haven't made much progress in this direction, we know that it will certainly require no algorithms because we know that for when epsilon is zero, so with no corruptions, we expect that the optimal algorithm is counting signed triangles. When epsilon is a constant, we know that optimal is the sum of square spectral certificate which we designed. But how do we interpolate between those, right? What if epsilon is 1 over square root n, for example? Likewise, we expect that also new lower bounds will be needed, right? In particular, because we don't even know how to prove the tight lower bounds when epsilon is zero in the case of no corruption. So we expect that somewhere in between also we need new lower bound techniques. The last question with which I'll end is related directly to the coupling, not the applications, and it's whether we can reverse. So what do I mean by this? Know that we present a polynomial time algorithm, which on input on Erdos-Renyi produces a random geometric graph with just slightly smaller density, which is contained in the Erdos-Renyi. Can we do the reverse? So if someone gives us the random geometric graph, can we output an Erdos-Renyi which contains our random geometric graph? Now, I'd like to know that this is actually purely an algorithmic question because we can always reverse the coupling, but can we do so efficiently? Thank you.